Good evening. Tonight we welcome Ed Daw, Professor of Gravitational Waves and Dark Matter Physics at Sheffield University. Ed specialises in ultrasensitive experiments, searching for the signatures of hypothesized and potentially critical signals in the field of particle astrophysics. In particular, searching for WIMPs, weakly interactive massive particles, gravitational waves and axioms. This is Ed's 7th visit to us over the years, going back to 2008. And these visits have included talks on gravitational waves and the playing of electronic synthesizers. So let's give a warm MSAS welcome to Ed Daw.
You are my favorite astronomy society, you know that. That's why I keep coming back. I love this little stuff. I think it's really nice, and you know, I see the same places again and again. So I feel like you're all my friends. So I'm really glad to be here. So I'm going to talk about axioms tonight. I've probably talked about axioms before, and probably some of it will be repetition. And it's actually the first thing I did research on when I started my career. And then I moved to gravitational waves, frankly, because there were no other axion projects, and I was bored with that one. And then I moved to WIMPs, and that was because there were no jobs in gravitational waves at the time. And then I moved back to gravitational waves because I decided WIMPs was a political morass that I didn't want to stay involved with. And then I moved back to axioms when gravitational waves were discovered, and it started to get a bit boring. So I'm back on axioms. And nobody knows if they exist. That's the first thing I should say. They're completely hypothetical. And the second thing I should say is I've got to do something to jazz up this talk. So rather than just saying the dark matter problem and talking about stuff going around galaxies, I will do that in a bit because that's important. I'm going to go way back, way back to the very beginning and talk about the sort of history of particle physics, because it's important to understand. Well, I think I can make you understand where axioms fit in. That's what I'm going to try and do. So we've got these rather boringly named standard models. There's the standard model of particle physics and the standard model of cosmology. So the standard model of particle physics is quite old, and it really goes back to the Greeks. And the Greeks had this reductionist view of the universe, whereby everything was supposed to be made of one entity called an atom. That's a way of simplifying the world around us, if everything is actually built out of atoms. It was a philosophical idea, and they had rather foolish notions of what the atoms were because they didn't have any data. But the sort of basic concept of large numbers of different varieties of stuff, actually all consisting of different aggregates of the same thing, kind of caught on. And it turned out not to be wrong. And eventually, the first people to make scientific sense of this was chemists who, you know, Mendeleev noticed that the different things that we found around us tended to share properties and could be grouped together into groups. And whenever that happens, it suggests that the groups are actually all the same because they share some common underlying structure. And that, of course, was atoms. And in fact, all the properties of all the chemical elements are derived from the arrangements of the electrons in the very outermost shells of the atoms. Even the electrons that are further in towards the nucleus don't really do anything active. They form closed shells and they're basically passive. It's only the few electrons in the outermost shells that define the properties of the elements, and you get some periodicity in the properties based on how many electrons there are in the outer shells. So the group 1 elements have 1 electron in the outer shells. The halogens have 7 electrons in the outer shell, and so on, one missing, right? And so that's very nice. And one thing you might notice about chemistry is that, of course, the atoms are composite. They're highly complicated objects, especially the heavier ones. You know, you've got maybe 90 electrons and 240 particles in the little hard nucleus in the middle. It's a really complicated thing. Yet, if you take 2 atoms of the same species and swap them, you can't tell. And it's not like having 2 Mini Coopers that are the same color, because they're very far from being identical. If you were to take a microscope, you could easily tell the difference between them. If you take 2 uranium atoms and you swap them, they're scientifically precisely exactly the same. The wave function that you get, some technical quantum mechanics thing, when you interchange the atoms, is essentially the same wave function, or maybe it differs by a minus sign, but mathematically they're the same. Yet they're complicated. You've got two complicated things that are mathematically equivalent. So in some sense, they're fundamental particles. Yet when you smash them into each other and break them up, you discover they're made of other things. And of course, that's exactly what the chemists and the physicists did. They broke them up, they discovered a nucleus, and eventually they discovered particles inside the nucleus, neutrons and protons. And their things got even more peculiar because in the nucleus, there were neutrons and protons. And those neutrons, for example, in the nucleus have been around for 13.5 billion years without decaying in the nucleus. But if you take one of the neutrons out of the nucleus and separate it, put it on its own, it'll decay in a few minutes. So somehow inside the nucleus, the neutron is a stable particle. Outside the nucleus, in that environment, it decays. That's very weird, difficult to understand. I'll throw something out there, which is kind of controversial. So imagine that the nucleus, inside the nucleus, is a particular state of the vacuum. You might think it's a very busy place, a nucleus, but imagine that the nucleus is a sort of background environment for the neutron that is a form of vacuum. And in that vacuum environment, the nucleus is stable. Its end state is less stable than its beginning state. It's going to stay a neutron. But if you take the neutron out of the nucleus and put it in the much lower energy vacuum of our ordinary roundest vacuum, that's what you get in a vacuum flask, the nucleus isn't stable, neutron isn't stable to that, it decays. And in between the inside of the nucleus and outside the nucleus, there's the skin of the nucleus, which defines a boundary between the vacuum in the nucleus and the vacuum outside it. And that would be called a domain wall. So domain walls are one of these things that people think don't exist because they show up in theoretical models of the universe as complicated mathematical structures. But if you interpret the nucleus, the inner environment of the nucleus, a vacuum state of one kind and the outside is a different one, maybe the edge of the nucleus, the skin of the nucleus is actually the wall between them. That's kind of a nice idea. Anyway, there's more trouble coming because if you bang together protons and electrons at enormously high energies, then you get reactions that imply that even the proton has a structure inside it, and that's, of course, quarks. So there's quarks and gluons inside a proton, and at very high energies, you can make those quarks interact as if they were sort of free particles, even though at low energies, they're bound very tightly inside the neutrons and the protons, and you can't separate them. So at different energy scales, you've got different fundamental particles. At very high energies, the fundamental particles are quarks, gluons, and electrons. It turn out they're pretty point-like. At lower energies, you've got nucleons, you've got neutrons and protons, which are bound states of quarks, but the neutrons and protons behave basically like fundamental particles. At lower energies, still, you've got a whole nucleus, behaves like a fundamental particle. At very low energies, you've got atoms that behave like fundamental particles. And there's really no difference between what makes a particle fundamental at a low energy and what makes a particle fundamental at a high energy. It's the same thing. This mathematical identicalness is really the requirement. And also the requirement is it's feebly coupled. So it sort of isn't strongly bound to something else. There's an analogy that's quite nice. So suppose you've got some really famous person like, I don't know, Queen. Well, we won't do the Queen, let's do the King. Prince Charles, the Queen's unfortunately gone, so we'll do Charles. So suppose he decides to walk across a square in London. Now, of course, people are attracted to Charles or maybe repelled by him, but there's bound to be a crowd gathers around him, right, as he tries to walk across the square. So he's not a weakly interacting entity, he's a strongly interacting entity. He immediately attracts a crowd of onlookers, and that makes it harder for him to move, so he moves more slowly, and this crowd sort of moves with him, and but if you take the crowd as a whole, it behaves like a weakly interacting particle. Why? Because somebody else might decide they want to get King Charles's autograph, but they can't get to him because there's already this big crowd around him, so they give up and walk away. And so once he acquires his entourage, he becomes weakly interacting. And that's a bit like how things work in physics, right? If you have a strongly interacting entity, it tends to nucleate a huge pile of crap around it, and then the huge pile of crap becomes the free particle. It's called a quasi-particle. So there's always some kind of things that behave like that are fundamental particles, but the things that behave like that depend on the energy scale. So what's this got to do with axions? So the idea is that axions are a particle which was formed in the early universe around the time that nuclei were formed. And it sort of happened in two stages. At very, very high energies, there's a thing called a phase transition. And it's a bit like the phase transition where the nuclei formed. You know, at high energies, there were no nuclei, they were just neutrons and protons. At low energies, they all clag together and you get nuclei. And at that sort of same energy scale, you get these things called axions. Now, why do we think they exist? Well, we think they exist because the very high energy universe, we think, violated a symmetry called CP. In other words, that's a symmetry where you switch all the charges on all the particles and you reflect the set of particles in a mirror. So that's a discrete symmetry. Both of those operations are discrete operations. Take the particles, turn them into quantiparticles, and then reflect it in a mirror. And if you do that with a physical interacting system, for a CP violating system, the system you get after that operation doesn't have the same properties as the system you started with. Right? Whereas a CP conserving system, it does. So a game of snooker is CP conserving. You reflect it in the mirror, you still get a game of snooker. Yeah, okay, the ball's in different places, but we'll ignore that one. Okay, so you have a symmetry that starts out in the high energy universe being preserved, and in the low energy universe, we measure things that violate, we measure CP conservation. We discover that this symmetry is conserved in the late low energy universe. And in particular, we do that by using the neutron as a probe. So the neutron contains quarks and gluons. We measure the neutron's CP violation. We discover it doesn't violate CP at all. So it's a low energy bound state, doesn't violate CP, but it's made out of high energy things that did. And the process of getting from a CP violating thing to a CP conserving thing involves a phase transition, which is not so different from a phase transition. And you can learn a lot from solid state physics. So suppose I've got some molten salt. They have that stuff in nuclear reactors. They use it to move heat around nuclear reactors. So you've got molten salt. You can imagine it's a liquid, it's hot, it's, you know, doesn't have any particular symmetry, and it's basically a sludge, a hot sludge of salt. And then you let it cool. And when it cools, it undergoes a phase transition. You have this beautiful crystal with planes of atoms. Everything's regularly arranged. It's a very, very different entity from hot salt, which is essentially a sort of boring homogeneous goo. Right? So between those two states of salt, there's a phase transition. In a similar way, between the high energy state of all these strongly acting particles and the low energy state, which is things like neutrons, there's a transition. It changes the properties of the theory. So when that symmetry breaking property happens, and there's loads of complicated maths, the idea is you get axions formed as a condensate in the theory. So low energy there's axions, at high energies there's no axions. So what's the other property of axions that's interesting? So you've all probably had talks from people who work at particle beam accelerators, right? Places like CERN. I'm sure one of the characters at Sheffield, Dan Tovey or somebody's been out here talking to you about fundamental particles at some point. So they're turned out to be a pretty lucrative business. It started after the war in the 50s. You discovered that if you bang together particles that you've accelerated, the energy that you've given them by accelerating them could be used to form new particles. So you whack things together at very high energy, you can make very high energy things. So you discover there's a whole slew of particles, some are called baryons, some are called mesons. They're all unstable. If you form these things, they decay again back into the normal particles that we sort of see in everyday life. And that's great. And that allows you to discover high energy states. But what would happen if it turned out that low energy particles with a very low mass, also had weaker couplings to other particles than particles with high masses? Right? Well, you in astronomy all know about selection effects, right? The things you study first tend to be the things you observe. If you point a telescope at the sky, first thing you probably look at is Jupiter, because the brightest thing, and you discover it's got moons. And of course, if you were an ancient and you didn't know about astronomy, you pointed at Jupiter first and you go, oh, look at all these moons. That's amazing. They must all be like that. And of course, that's wrong, because most of the other stars are not planets. They're very different. You know, it's a selection effect. Looking at the bright things first doesn't necessarily give you an unbiased picture of what the world's like. And it's exactly the same, perhaps, in particle physics. So the first things we've found have been high energy states by using accelerators. But what if there were things which accelerators couldn't see? Because they're very low mass, and the theory predicts that some of these very low mass states might have very small coupling. And therefore, they wouldn't have been observed in accelerators, but there might still be a lot of them about. And there might be lots of different kinds of these low mass particles. And so people talk about a thing called a hidden sector. The idea is that there's a lot of stuff out there that we haven't found with our accelerators because we're suffering from a very severe selection bias. We've discovered the easy stuff, but we've missed the subtle things. And axions are one of the examples of these subtle things. So very light, therefore very feebly coupled, therefore also very difficult to detect, but possibly very numerous, lots of them about. And if they all have a mass, see, so if these things formed in the early universe, very light, very hard to detect, but enormously abundant, perhaps the hidden sector solves the dark matter problem. Perhaps in some sense, a galaxy is actually an assembly of an enormous number of hidden sector particles. They're all massive, therefore the thing nucleates around a slight excess of mass in the usual way. You start with a small excess and you end up with a big excess, and eventually you've got a galaxy. And the stars and the stuff we can observe gravitate towards it just like everything else. So we see the beautiful spiral galaxy or the elliptical galaxy, but what's actually there is embedded in this galaxy is this enormous amount of dark matter. And it could be axions and other things like them. Can't remember what's on this slide. Yeah, so high energy, Big Bang, early times, very high energy theory, CP violating, everything's chaotic, everything's crazy. Then you have a phase transition and you form quarks, gluons, electrons, and photons. That phase transition is hypothetical. It's called the Petro-Quinn phase transition. Then at a lower energy, you have another phase transition called the quantum chromodynamics phase transition. And that's when you make your neutrons and your protons. And then at very last low energies, you end up with atoms and kind of the world today. And this cascade of phase transitions gives rise to axions at some point. And they're just around. And once they're formed, the universe expands. They don't interact with each other very much. And they're just still here. They've been around since very early times. They're just still about. And they aren't doing anything. They're rather boring. The only thing that they do, you can observe, is they have gravitation. So they form conglomerates and assemblies, and those we call galaxies. And so the other reason that all this stuff is attractive is because we know there's a lot of matter in the universe that we can't see because of the normal stuff that everybody talks about dark matter talks, which is that galaxies rotate, but they don't rotate the same way solar systems do. So in a solar system, the velocity of rotation of a planet is proportional to 1 over the square root of its distance from the sun. The further it is away, the slower it's moving. So you'd expect galaxies to be governed by the same mechanics that gives rise to them. Turns out, clever. Sorry, everybody at home, that got a horrible deafening funk just then. My microphone decided to fly off because I was gesticulating wildly. Galaxies, if you naively assume that the galaxy is dominated by the mass in the central core, which looks from a telescope as if it's where all the mass is, then you'd expect that the rotation velocity of the gas and dust around the galactic center, once you got outside the core, would drop off in the same way that the planet's velocities fall off with their distance from the sun. And it turns out that that's not true when you measure the rotation, which you do with hydrogen alpha, use radio telescopes and a Doppler shift to get a rotation velocity. It's not an easy measurement. It's a huge radio telescope to do it because you need the resolving power to take lots of samples out along the galactic disk. You discover that actually the rotation is flat, and it doesn't matter what radius you are from the galaxy, you get the same velocity. Of course, that probably doesn't go on forever. Eventually, you get outside the core of the galaxy. It's just the core of the galaxy is a lot bigger than it looks. So the dark matter hypothesis is that the reason for this is there's loads of other particles in the galaxy that you can't observe, and maybe they're axions. And the hardest thing about this talk is that everything sort of makes sense except the axion, because I've had to sort of pull the properties of the axion out of the air, because I'm not teaching you quantum field theory. You'll thank me. You don't want to learn it. The point is that the axions are predicted in this symmetry breaking mechanism called the Petro-Quinn mechanism, and Petro and Quinn are theorists. I actually know them both. Helen Quinn's actually still about. She's in California. Robert Petro is no longer with us, but he was a very nice man. Always wore Hawaiian shirts. I rather liked him. Anyway, so the axions got properties, and the properties, as particle physicists like to do, are expressed in terms of these Feynman graphs, which basically tell you how axions collide with things. So it is an axion, it collide with it can collide with an electron. You can think of this as an electron. And the collision, the simplest kind of collision, is just a single vertex that just goes bang, bounces off it, right? And then out of this vertex, you can make other things. So an axion here is colliding with an electron. The electron's going around in a loop, and it becomes an anti-electron at some point, so it can go backwards. And eventually it also connects to these two other vertices, and these are photons. So that's the most useful interaction of an axion. It has a coupling to two electromagnetic waves, and that makes it detectable, right? So the detector was actually dreamt up by this chap. That's Pierre Zakivi. He's at Florida. He's another very nice man. I met him 33 years ago. I don't see him very much because I don't have enough money to go to Florida. I wish I did. It's very nice there. Anyway, he had this idea for a detector, even though he's a theorist. The best theorists think about experiments. The ones who never think about experiments are not so useful. The ones who sit down now and again and think about experiments can be very useful. So he had this idea for an experiment. What you do is you take a resonance structure that's electromagnetic. So you use an empty metal box, or maybe you put something inside the box that you can move around. It's a tuning element, actually. It allows you to tune it. And then if you get, and then you thread the box with a big magnetic field. And the idea is an axion that's in the halo of the galaxy, it's just around you. They're everywhere, these things, right? The idea is they're everywhere. I mean, there's a lot of bold assumptions in this kind of experiments. But one of the bold assumptions is that there's as many axions here as there are anywhere else in the galaxy, in this room, all around us. Number density of maybe 10 to the 13 per cubic centimeter. There's a hell of a lot of them. Or there's none. I mean, it sort of depends whether the theory is right or not. If you get the frequency of this resonance right, the axion will sort of bounce off the magnetic field and produce radio waves. Because it turns out the axion mass may be about the right kind of mass for its energy to be converted into electromagnetic waves at the energy that corresponds to radio. So you get a few hundred megahertz or a few gigahertz. Okay, and then you have a receiver. And if some of you may know about radios, sort of thing you find in Astronomy Society. Maybe if I was at Jodrell Bank, there's an Astronomy Society just down the road from there. You want to watch it if they ask you to give a talk, because there's some pros in the audience. Make sure you don't want to say anything wrong at that one. So maybe some of you guys know about radio. So a heterodyne receiver, you basically amplify, you mix down to a lower frequency, you amplify again, you filter, and then you put it through a speaker and you've got a radio. That's an AM radio circuit. FM radios work a bit differently. They use a thing called a phase lock loop. It's a bit more complicated. Anyway, so axion, the receiver, is very like an AM radio, except instead of a speaker, we acquire data. And then in the data, you hope to see evidence for an axion signal. And if you want to know why you need this cavity, think about two tuning forks separated by some distance. So if I whack one of the tuning forks, the other one will start resonating if it's at the same frequency, because there's some weak coupling that goes through the air. And in exactly the same way, you can think of an axion producing a wave inside the cavity, and the cavity vibrating in sympathy with the wave produced by the axion. So that's sort of how the detector works. This is a big one. So it's the one I got my PhD on. This is called ADMX. And you can see that's the experiment. The magnet is actually in the floor. So the magnet's 4.5 meters high, and it goes down into the basement. And they've got it on a crane, and they're lowering it down into the hole, and it'll sit with the cavity, which is inside this copper can, inside the bore of the magnet. So the magnet's basically a solenoid, so it's just wound like any magnet. You could make it yourself. I mean, they're kind of fancy magnets because they have to have quite high fields. So the easiest way to do that is to have a superconducting cable, so then you don't have any electrical losses. So that means it has to be kept very cold. But it turns out the cavity has to be kept cold anyway, because the colder it is, the less electrically noisy it is, the more likely you are to be able to detect a signal. So having it cold is necessary anyhow. So the whole thing is kept cold. The magnet's kept cold, the cavity's kept cold. This experiment runs at about 150 millikelvin, 0.015 degrees centigrade above absolute zero. So it's pretty cold. And it's big. You know, this experiment is the one I did my PhD on. Looks a bit different now than it used to look when I was a student. It's also moved. It used to be at Livermore Lab in California. Now it's in Seattle, a place called SENPA, which is on the campus of the University of Washington. And if you break it up and look inside, you can see it's kind of an old-fashioned experiment in that it's cooled actually by liquid helium. There's an awful lot of liquid helium. The magnet sits in liquid helium, and the cavity doesn't sit in liquid helium. It sits in helium vapor, but the presence of liquid helium around it keeps the temperature down. And then finally, there's a thing called a dilution refrigerator, which is connected up here above the cavity, and that uses helium as well, but it uses it in a configuration that I don't know how much time I'll have to explain it. I might try and explain a dilution fridge. It cools things further down. Ask me afterwards if you're curious how a dilution fridge works. And that's how they get down from 4 Kelvin, which is kind of natural temperature liquid helium, to about 150 millikelvin. And they can't get that much colder than that. And so this is the sort of slightly more complicated version of the electronics I showed you on the last slide. It's pretty much the same thing. And then the critical thing is how noisy the first amplifier is. So this is the type of an amplifier called the Josephson parametric amplifier, which can have a noise temperature, again, of about 100 or 150 millikelvin. So it's very, very low noise, and that's what it looks like under a microscope. It's kind of a fancy thing. So that's ADMX, and ADMX is the world's leading axion search. They haven't found any, you know, hard, maybe they don't exist. And what physicists love to do is make these parameter spaces with the possible properties of the particle on 2 axes. So in this case, you've got the mass of the axion on the horizontal axis and its coupling to photons on the vertical axis. And we think that those 2 things are related. So the yellow line is the relationship between the mass and the coupling. So the heavier it is, the more strongly coupled it is. Remember, I told you that lighter particles are harder to see, so that makes sense. The lighter the particle, the harder, the smaller the couplings get. And then these experiments like ADMX are looking here, and this is the region of everything above the red they've ruled out, and they're actually succeeding in probing the axions where we think they actually are. And then there's all the other experiments that are placing limits on things, but they're not axions. Those are things called axion-like particles. An axion-like particle is an axion, but with a stronger coupling, sort of a cop-out axion, easier to see axion. So these resonance experiments are really the only one that succeeded in probing the axion. Now, you can see an enormous range of masses here. And I think most of those masses are not really physical. I don't really believe that axions are lighter than about 10 to the minus 6. Other people do. I think they don't. Axions that were lighter than 10 to the minus 6 would have had to be formed before the inflationary epoch in the universe ended. I just don't buy it. So I don't really think so. And the other thing is that axions, as you go this way, there's nothing wrong with those axions except that they form less and less of the dark matter. So as you go up this way, axions go from about all the dark matter. By the time you get to here, they're 1,000th of the dark matter. So really, you want axions to be down here. So ADMX are looking in pretty much the right place, I think, at the moment. So they could actually be discovered in spite of this enormous parameter space, I would argue. So back to Britain, right? What have we got in Sheffield? Well, what we've got is a baby ADMX. So a few years ago, the UK sort of woke up, smelt the coffee, and realized that maybe WIMPs don't exist. I mean, WIMPs have been the most popular dark matter candidate since about 1985. And that's because they are at high mass. You know, WIMP masses are about 100 giga-electron-volts. They weigh about the same as a heavy nucleus. And they are stable in spite of that, which is, to me, rather unnatural. Heavy things decay usually. Well, heavy nuclei don't decay, so there are exceptions. But you know, so anyway, they were the most popular thing simply because other things were discovered there. So the W and the Z bosons were discovered at 85 and 90 giga-electron-volts. So the idea is, well, maybe WIMPs are part of this same stable of particles. Maybe you can solve the dark matter problem with electroweak physics. That was the idea. So there's a lot of people who went to town on that, built these WIMP detectors, and then people built higher energy accelerators and actually expected to discover more new physics at high energies, and didn't. We discovered the Higgs boson, but we already knew that was there. Supersymmetry didn't show up, neither did anything else. So that rather suggests there isn't much going on at high energies apart from the W and the Z, and God knows where. I mean, I'm sure at some other much higher energy scale, there'll be an explosion of new physics, but not at the electroweak scale. So that caused there to be a sort of increase in interest in axions, because they don't rely on the electroweak scale at all. And in about 2017, I started getting invited to give a lot of axion talks. Before 2017, I didn't give one for about 10 years. Nobody cared, right? Just nobody cared. And then all of a sudden, I started getting invitations, so I knew something was up. And then before long, people were coming up to me and going, we should write a proposal. You know, I literally started nucleating. I became a strongly interacting particles. And all these physicists started coming up to me at conferences and going, I want to help you. And this had never happened to me before. It was like, so overnight turned into this guy who was going to lead something. Unfortunately, the University of Sheffield was on strike. So I had time to write the proposal. Amazing how things work out. I told them after I got the 5 million quid that they should just send me home permanently. I'll sit in my living room and just write proposals. They're much more useful to you there. That's a bit of a joke. I would hate to do that. And the 5 million quid, by the way, didn't all go to me. That went to 6 or 7 different institutions. We got 1.6 million, and we used 0.9 million of it to buy this thing. So this is a dilution refrigerator, which was made by Oxford Instruments, and it gets down to a temperature of 10 millikelvin. It's more modern than the ADMX one. ADMX's unit consists of all these liquid cryogens. Nowadays, that's not the way things are done because liquid cryogens have got very expensive. You don't want to run a fridge that way anymore. So we use mechanical cooling to get us down to 4 Kelvin, and then a dilution refrigerator that works rather better than the ADMX one to get us down to 10 millikelvin. And we've got a cavity, but it's not as big as theirs because we couldn't afford the giant cavity. And the magnet's smaller as well. But we're looking at higher frequencies, so things are naturally smaller because higher frequency means shorter wavelengths, so everything gets smaller. And then basically it bolts up and looks like a giant capsule that you take for indigestion, but inside there's multiple layers. It's sort of an onion, and as you go in, you get to lower and lower temperatures, and right in the middle, it's at 10 millikelvin. And there's the cavity in the bottom. It's mounted on a little copper frame. We designed its whole support structure. That was all designed by Trevor Gamble, who's an engineer at Sheffield, and made by a company called M&J Engineering, who are in Penistone. And that's the magnet. That's a 400,000 pound magnet. It's a beautiful magnet. It was made by Oxford Instruments. It's absolutely fabulous. It has an 8 Tesla field, but it's shielded, so you can stand a meter from it with your pacemaker in your chest and not worry. And that's just fabulous because it's not just people who can suffer from magnetic fields, it's also equipment. So all the other stuff in my lab doesn't have to live in a giant stray field. And that means things can be closer to the experiment, all the cables can be shorter, and that makes everything work better. So that's a terrific thing. And here it is getting cold. So it takes quite a while to get cold. So this is temperature on a log scale, so 100, 10, 1, 0.1, 0.01 Kelvin. And this is days. So it takes us about 6 days to cool it down. And the magnet has to go down to 4 Kelvin. The cavity goes down to about, actually it goes down to about 20 millikelvin. This thing up here, the cold plate, the mixing chamber plate, that's the thing that gets to 10 millikelvin. So that's evidence that we can cool it. And then here's some of the gang. That's Mitch Perry, Paul Smith. This is a guy from America called Nick Dew. This is Claude Mostyn, and that's the experiment. And actually, we were at the time testing an aluminium cavity. This is work we did with the Americans. So we're working with ADMX. They're our friends. We collaborate with them. Actually, it's really great because we taught them some engineering. Yeah, because the thing is, American physicists have a weakness. They think they can design everything themselves. But we have actual engineers that work for us. So it turns out they may have a lot of money and have lots of clever physics ideas, but we know how to make a bearing to support a cavity on a spindle. It turned out that our support scheme was better than theirs, and so they've adopted ours. So we're teaching them a few things. They're teaching us a lot of things too. They taught me a lesson I should have learned by now about nitrogen ice a couple of weeks ago. So you have to be very careful when you have an experiment that you cool that once contained nitrogen, because nitrogen's a gas at room temperature, but at below 30 Kelvin, it turns into ice. And that can get in, the mechanisms that move the tuning rod can literally ice up. And I learned that from Dave Tanner at Florida in a meeting with those guys and went, oops, nitrogen ice. So we warmed our experiment up. And when it got to 30 Kelvin, everything unjammed. Just the ice melted, that's all it was. So, we're learning from each other. So this was an experiment with an aluminium cavity. Aluminium has the property that it superconducts at very low temperatures, so all the electrical resistance goes away. But the problem is that in the magnetic field, it quenches. So it's not, you can't run a superconducting cavity, but what you can do is coat something with a superconductor that is tolerant of high fields. So there's this material called niobium tin, and actually part of the magnet's made out of niobium tin. And niobium tin alloy has the property that it tolerates a magnetic field. So we wanted to try and test that. So the tuning rod inside this cavity is actually solid niobium and coated with niobium tin. And this is a horrible, complicated plot. So the black line is the magnetic field going up. So the magnetic field's here in Tesla. So this is 6 Tesla. So at the time, we didn't have the guts to run at 8 Tesla. We were only running at 6. And what's interesting is the quality factor of the resonance, which is basically how lossy the resonance is. The higher quality, the lower the loss. And you'll see this is the loss, and it goes up in steps as different things become superconducting. So this is a niobium tin, and then the niobium, and then the aluminium starts superconducting. So this is very high quality. And then you turn on the magnet. As soon as you turn on the magnet, the aluminium quenches and stops superconducting. And then you ramp up the magnet some more, and you discover that even at 6 Tesla, the thing still hasn't dropped to where it started. This means the niobium tin coating is still superconducting. So this demonstrates that this coating allows us to run a superconducting cavity in a high field. It's not perfect, but this is all going to get published. So this was our first work with ADMX. This is the first thing we really did after we got the experiment, and it's going to be a paper soon. And then there's the question of how things you have to move is you have to be able to move the tuning rod around inside the cavity. And you also have to be able to put the field probe that goes into the cavity to measure the electric field has to be able to go in and out. So those two things are both done with piezo drives. And the question is, how do you, the piezo drives rotate. It's a cold motor. It's a motor that can run at 4 Kelvin. It goes round and around, and you've got to turn that into translation motion. So the way you do that's just with a screw, just like you would with a bolt. You turn it around and it goes up and down. So this is one that Mitch Perry made. He's my student. It's a nice mechanism that he built, and that's it installed. And it works now, so we can move the tuning rod in and out. And then the next question is, how do you run these very low noise amplifiers? Because they don't like magnetic fields either. So for that, we've got these friends at Lancaster who designed this little can, which sits, this is the cavity down here, the can sits above it, and the can consists of layers of superconductor, layers of niobium, and in between them, you've got layers of a thing that's basically iron. It's called, what's the stuff called? Cryoperm or something like that. Anyways, it's layers of that and then layers of niobium, and inside this thing the magnetic field's down at maybe 10 nanotesla, so you can run a field intolerant piece of electronics inside this box. And because the magnet is shielded, the box itself can actually be quite close to the cavity, which means the connecting cable's relatively short. It means you're less likely to have trouble with things called standing waves, which are a real pain in the neck at microwave frequencies. And that's just some more pictures of inside the apparatus. So these are the two motors. These are the piezo motors that drive things around, mounted on this metal plate. These are the axles. You're looking up into the motors from below. Those are the axles that go and connect to the tuning rod and the antenna. And it's just a mechanical mechanism. They're made of G10, which means they've got low thermal conductivity, so you can have the motors at 4 Kelvin and the cavity at 50 millikelvin or something. And you don't have to worry about too much heat traveling up and down the axles because they're made of an insulator. It's not perfect, but it's a sort of stopgap solution to, I think, of a better one. So all that engineering is kind of done, and we can move the tuning rod, we can move the antenna, we've got an amplifier, we've measured the noise. So this is noise versus frequency. All these nasty zigzags are standing waves, so we've got some work to do to get rid of those. But the basic noise temperature of the apparatus right now is somewhere between 2.5 and 3 Kelvin at a frequency of 5 gigahertz. So we're going to basically measure power in this cavity as a function of frequency and then tune it. And as we tune it, if the axion shows up, we'll see excess power. And then if it's really an axion, then if you turn the magnetic field off, it should go away. See, so that's the advantage we've got over the WIMP people. If we see a signal, we have a way of controlling the signal power. Whereas if you have WIMPs, you just get some number of counts a day, and there's really no way you can turn it off. It's just a different kind of signal. So this is a sign that we're about to take data. Yeah. So who knows? I mean, it's not very likely we'll discover anything. We're not very sensitive right away, but at least we've got an experiment. At least it's running. And then the next stage is to go to a low noise amplifier. So these guys at Oxford have made us this thing called a standing wave parametric amplifier. Here it is. So that's going inside the box I showed you a couple of slides ago. And then we've got to learn to run that amplifier. So I shall have the guy that built it come up from Oxford and give us some lessons in running it. It's not a trivial amplifier to run. And then this is a demonstration from my student Claude that the little piezo motors I show you can actually tune the resonance. So this is the resonance of the cavity. And Claude is making 25-step motions of the twisting the antenna around. You can see you can gently move the resonance over. So you've got enough control to move the resonance. It's direct drive. There's no gearbox. That's the wonderful thing about these piezo motors, is they give you exquisite control. They aren't very high torque, but you can be very gentle. So they're very useful from that point of view. So, okay, I probably rabbited on for long enough. These conclusions were not made for you. They were made for a bunch of physicists in France last week. But so the big experiment, ADMX, one I showed you that I used to work on, it's doing its thing. It's going and writing papers and excluding parameter space. Relatively low axion masses, maybe about 3 microelectron volts. We're going to be looking at 25 microelectron volts. So we're a new experiment. We've only really had the apparatus for 2 years. The fridge arrived in about April 2024, and we were an empty lab at that point. So we've started from absolutely nothing. ADMX has been around for 30 years, so they definitely had a bit of a start on us. We've done some tests of these field tolerant superconductors. That might be something we use, or maybe not. I've actually got a different idea of how you can tune much faster, but it's a bit controversial, so I'm not sure I want to throw it into the world until I'm sure it works. I should really make sure I know what I'm doing before I start publishing that. We've managed to find out why our equipment's jamming. It's nitrogen ice and a few other little problems, so hopefully that's behind us. So we're literally about to start taking data. We've got one more test run to do, and then we'll turn the magnet on and start looking for axions. And hopefully my Christmas present will be our first sensitive data. And then it's really a Christmas present for the student, because the first student's supposed to graduate by April. So he's agitating for data quite reasonably. So that's really his Christmas present, not mine, but it's mine as well. So yeah, I mean, I know this is a really technical talk, and there's loads of particle physics and crazy stuff that I probably shouldn't even talk about, and it's not astronomy. It only becomes astronomy when we detect it, because once you have the axion's signal characteristics will tell you all about the galaxy and probably about the early universe as well. So it's one of these very, very high risk and potentially very rewarding things that could all turn out to be nonsense. And the only thing I will say is the apparatus I've got kind of resembles a quantum computer. So as we're studying the noise backgrounds in this experiment, we can perhaps communicate with that community as well. So even if the axion work turns out to be boring, which it is if there's no axion, at least we're still doing some science that some other people might take an interest in. That's what I hope anyway. Yeah. And of course, I've got plenty of time to answer questions. So if you have any questions, I'll be happy to try and answer them. Yeah, thank you.
Ed, what an extraordinary talk. At least I'm going to be able to listen to it again several times over the weekend and try and
pack a bit of a punch, that talk, doesn't it? Well, the beginning bit with all the particle physics was posed for Oxford undergraduates, because I got asked to give a talk for the Oxford Undergraduate Physics Society. So I had to make a real splash, so I decided I'd go and do the sort of try and do the everything talk. That's where that all came from. I hope it's right. I think most of it is.
Okay, so as usual, if you are online, then can you put up a digital hand? If you're in the room, attract my attention, please, in the usual manner. While people are thinking about questions and the like, just a quick one from me. You were talking about neutrons being outside the nucleus, and after a few minutes, they decay. Do protons do the same thing?
Neutrons decay into protons.
Oh, okay.
Yeah, a neutron decays into a proton, an electron, and a neutrino in free space. And people just take that for granted. But I think it's enormously... Actually, the person who got me thinking about this again was an undergraduate in a lecture. I teach first year, and I taught this first year course, and I remarked that the neutron was unstable outside the nucleus. And the student went, "Isn't that weird?" And looked at me, and I thought, "Yeah, it is really bloody weird." And it got me thinking about it, and it made me realize that perhaps it's the environment that determines the stability. So maybe you can think of the environment in a nucleus as a different kind of vacuum. It doesn't look like a vacuum today. It looks like a very violent environment, very high temperature. But on the scale of the temperatures during the Big Bang, it's bloody freezing. So maybe in some sense, the inside of a nucleus is a fossil vacuum state from the early universe. It's a nice thought, isn't it? Just got me thinking about it. Because people always say there are no domain walls in the universe. What happens if they're all around us? What happens if every atom's got a domain wall in it? It's kind of a different way of interpreting the stuff. Yeah. I don't know whether it's right.
In the room, Tony Morris. Have you got a speaker?
Yeah, on your diagram of the detection phase space,
Yeah.
where does your experiment?
Oh, good question. Yeah, yeah. Okay, so we put me back. Yeah, put me back.
Yeah, put you back. Right.
Yeah, that's it. That's what everybody always wants to know, and I'm always reluctant to, I want to publish a paper before I put us on the face space. A lot of other people will say this is where we're going to be, and I don't like that way of doing things because it encourages exaggeration, doesn't it? And I don't like it. But okay, so where they are is down here, which is at about
Ed.
few microelectron volts.
Ed,
Yeah.
could I just ask you to use your mouse pointer to point?
Oh yeah, oh yeah, okay, that's a good idea. Right, I've got to try and do this now. Okay. Where's my mouse? Is it here? There it is.
That's mine. That's yours.
There's
Right.
mine. All right. So now I have to try and back to the right slide. No, that one. So we're going to be probably in this kind of gap here initially, and not as good as this yellow stripe. So you see where my arrow is? We're probably going to be about there to start with.
So just outside the
Just that, not quite exactly, yeah, because the problem with my experiment, the way it's built, is that, I asked for a huge amount of money from STFC. I wanted 12 million, and I got 5, which was amazing, but it wasn't enough to build a very big experiment, so I built a little one. So I haven't focused on sensitivity, but I focused on its tunability. The cavity can actually be tuned over a big range because it's got this big tuning rod inside it. So we can go all the way from something like 16 microelectron volts to about 33, which is a big search range. And ADMX has done a fraction of that in 30 years. So we can potentially cover a much bigger range, but not at such high sensitivity because it's got such a small volume. So I've actually got a cure for that. And the cure is to dump the tuning rod, and immediately the quality factor of the cavity goes up by a factor of 10 because the tuning rod's a perturbation on the shape of the cavity and it ruins the quality. And then replace the high quality, and instead of tuning with an actual physical rod, I use a circuit that takes power out of the cavity and actually regenerates it and puts it back in. I've got this feedback technique for making resonances where they otherwise don't exist. And because it uses an external circuit, I can tune it with a computer instead of having to move something around, so it's simpler. And also I can have multiple resonances, so I can basically have multiple experiments inside my cavity. So that's my plan to go faster, is to do everything that way. And if it works, it's great. Everyone will be doing it next year. But I've got to make it work. And B, I've got to convince everyone it's not crap. Because whenever you have a completely new way of doing something, the first thing everyone says is it doesn't work. So I'll have to deal with the naysayers and the skeptics. But, that's my plan. So I'm going to try and get sensitive using that technique. Even though I'm quite small but feisty, basically.
So what you're saying is you're going to push the Q right up with your resonance?
So imagine what it's going to look like is there'll be a kind of a lazy Q, which is the cavity itself. And then on top of that, there'll be some spikes, just super narrow. I call it the crown of thorns plot. I want to make this plot where the characteristic of the cavity looks like a picket fence or a crown. And every one of those narrow peaks is an axion detector. That's how I want it to work.
Like a cone filter.
Yeah, exactly. And then you just take the whole thing and move it along, but you're looking at 100 frequencies at once every step. That's exactly what I want to do, yeah. Cone filter is exactly what it is. Now, that's what I want to try.
Okay, Tony.
Yeah, thank you.
Well,
Okay. Online, Mike Scollan. Evening, Mike.
Evening. Hi, Dr. Ed.
hello, Mike. I think I've met you many times.
You said early on in the talk that all atoms of the same element are identical.
Yeah.
Does this mean that protons and neutrons always align in the same pattern? And how has that been proved?
Well, the thing about atoms is you have the vision of them kind of consisting of particles that are all in a sort of snowball with all clagged together. But you can't observe an atom. You can't actually see it with glasses. You can't reflect light off it and observe its detailed structure. So that detailed structure is just a sort of empirical model. It's not really what they're like. That the quantum mechanical representation of atom is with a wave function. And the wave function doesn't allow for actual positions of things in the atom. That's just not information you can get. It's a little bit like the image of a hydrogen atom being a proton with the little electrons orbiting around the outside. It's a nice picture, but it's not accurate. It's a model that has purposes. You know, the Bohr atom can correctly predict the energy levels of a hydrogen atom, sort of approximately, but it falls over for the other atoms. And you can't, you know, if you can't observe it, there's no real sort of meaning to it. You know, that's the usual rule with physics. The only thing that matters are things you can measure. And I think I don't think actually, in fairness, it's a good question, Mike, because I don't think anybody really has an accurate wave function for an atom. But the idea, the quantum mechanical idea of them being identical, I think is something that everybody accepts. I don't think they behave like classical objects in any sense. I think they are really. So
it's the wave functions that are identical.
Yeah, that's right. That's right. So, you know, it could turn out one day that wave functions aren't good descriptions of atoms, but at the moment they're the best description we've got, so we'll go with them, you know.
Cool. Thank you.
I'm looking around for other questions. Graham?
Is there any known or accepted particle which can be injected into your apparatus to test it in a simple way?
Yeah, that's a really good question. So, yeah, I mean, so we can test a lot of it by injecting electromagnetic waves, because they're known. So, you know, the simplest thing you can do is just inject a sine wave. That's probably what we'll do first. In fact, we already do that. We want to find the resonances of the cavity. We put in a swept sine wave, and if you hit a resonance, you get a peak. So you basically get the spectrum of the cavity. If you want to pretend you've got an axion, then what you need is some more complicated signal that replicates a signal whose frequency spectrum looks like a sort of Maxwell-Boltzmann distribution. It kind of goes up and comes down again because it reflects the sort of thermal distribution of the energies of the axioms in the dark matter. So you can make that using a waveform generator. And I've got an undergraduate student actually working on that right now. We've got quite a complicated circuit board in our lab that I've had for a few years, not really knowing what to do with it. And then this second year undergraduate, very, very keen girl came to me and said, I really, really want to do a project in your group. And I thought about this circuit board, and I knew that some group at Fermilab has written some freeware for it. So I let her loose with the board, and she downloaded the freeware, and she's got it all going. And hopefully she'll be able to make a fake axion generator out of it. We'll use that to put signals into our cavity. In terms of injecting something that's actually a particle, the problem is that because of this effect I told you about, there are no particles that we currently know about at a mass of a microelectron volt. If there are, we can't detect them. So we're kind of stuck with the heavy stuff that we know about, which is physically very different. The closest thing to an axion is probably a pi-zero meson. But the pi-zero meson has a mass of 130 mega electron volts, whereas the axion maybe has a mass of about 1 micro electron volt. So that's a difference of factor of 10 to the 12. And that means that they have completely different properties. So we couldn't get a pi meson to take any interest in our cavity. So we're stuck with pretending we have axions using electromagnetic waves, because they have zero mass. So that's pretty close to 1 micro electron volt. So, you know, electromagnetic waves are pretty good surrogate. Not perfect, though. I'd much rather do it with a particle. I did think about whether you could do it some clever way. I haven't thought of a way yet, but it would be much better if we could. I agree. It's just there isn't a state that I know about that has the right properties. That's the trouble. But it's a good idea. Oh God, it's super expensive. Yeah, but it's not that bad. It's 900,000 quid. It's actually cheap for a physics experiment.
Andy.
Hello.
Inside the actual chamber where you're taking the vegetable. Inside the actual chamber we're taking the resonance chamber, is that under vacuum? And if so, what level of vacuum is it at?
So we get down to about 1/10 of a torr, so 10⁻⁶ atmospheres. And then after that, we're very cold. So there's a cryopumping effect. So at about 10⁻⁷ atmospheres, all the sensors give out, and I don't know what the vacuum is, but it's better than 10⁻⁷ atmospheres. It's like flypaper, you know, cryopumps are great. If you've got a cold experiment, after a while, you don't have to worry about gas anymore because it all just sticks to the walls. You do have to worry if it's polar stuff. You don't want water because water molecules are polar. So if you're doing electromagnetic stuff, you don't want that stuff hanging around. But nitrogen, helium, they're all fine. Yeah, it's a very good vacuum.
Okay, Andy. Mike Scotland wants to come back online. Mike.
Mike.
Yeah, hi again. The neutron instability. How can we explain the presence of neutron stars if neutrons are so decay so quickly outside of the
neutrons?
nucleus?
Yeah, that's a real good question. So neutron stars are basically just like a giant nucleus, and you end up with this enormous aggregation of. So I guess I'd argue the inside of a neutron star is a very large vacuum of the type I was describing earlier. It's a seething, bubbling mess that neutrons are happy stable in. They just don't want to decay into anything else in that environment. Actually, it makes sense because if you have an excess of protons in a neutron star, why is there so many neutrons in a neutron star? It's actually a really good question. I think it's the charge. I think if you have too many protons, you have the energy level goes up just because of the electrostatic repulsion of all the positive charges. So at that kind of level, or it may be this. I can't remember my nuclear physics. I can't remember why neutron stars are all neutrons. I confess I can't remember. That's something I can't remember.
Does it indicate some kind of link with the weak or strong nuclear force?
Well, it might, yeah. I mean, like I said, I can't remember. So they're all around as well. Strong nuclear force is what binds the neutron star together. All right, that's what allows them to form this big conglomerate. It's definitely connected to that. The weak nuclear force, I don't think will play a role. Gravity plays a big role. You know, that's a big force that's pulling everything together as well. And eventually, gravity wins, and the neutron star implodes, and then you get a black hole. That happens as well. So it's interesting stuff. I mean, I'm just about to get very interested in high energy sort of nuclear physics because I'm wondering if you can find evidence for axioms by looking at accelerators that collide heavy ions together because of this idea that maybe, you know, there's different vacuum states, and some of these vacuum states that are produced in nuclear matter might tell you something about the axioms. So this is something I'm thinking about, trying to make connections with my particle physics friends. You know, this particle physics is struggling right now because they haven't discovered anything in quite a while. And people are wondering if they should pay for the future circular collider, you know, because what the hell are they going to see there? I'm wondering if the next big thing might be very careful examination of heavy ion collisions, because you can learn a lot about these interesting nuclear matter states, and they're all connected to axioms. So I wonder if I might learn something from the data. But that's a hobby at the moment.
Okay, Mike. Just
on, is it for the neutrons and neutron stars, is that the reverse of the decay of the neutron?
It actually might be. It's inverse beta decay. Yeah, that rings a bell. Actually, that's how you end up with all those neutrons. Yeah, I think you might be right. But I'm on shaky ground. It's not my field. I know I've got myself into difficulties by talking about things I don't know about.
Well, you start to sound like a historian now. So we'll move on. Sheffield doesn't strike me as a place to have a very delicate instrument. Do you have problems with sort of physical vibration and the rest of it?
Yeah, not really. It's funny because you're protected by the frequencies where you're working. You know, I'm working at 5 gigahertz. Seismic noise tends to cause trouble at 10 hertz. There's a factor of 10 to the 9 in frequency in those two. But the only thing that you do have problems with is with things like temperature sensors, which do pick up vibrational noise and the consequences of that. So you do worry. The other thing is heating. You know, things vibrate. You're trying to operate at a very low temperature. Any sort of friction, vibration can translate into excess heat. So you don't really want things to be shaking like a jelly. but I haven't had to buy special vibration isolation systems for my cryostat, which is a good thing because I couldn't afford them. I mean, LIGO, the gravitational wave stuff, you worry about that stuff all the time, but that's because your signal's at 1 kilohertz. So that's right in the middle of the acoustic band. So you really have trouble with vibration there. But once you're at a few gigahertz, you don't really have to worry about it so much.
Mobile signals.
They cause trouble. So I've had, my lab doesn't have any Wi-Fi in it. I've got rid of all the Wi-Fi routers and, you know, so yeah, they're in the right place. But fortunately, the experiment is in several layers of metal. So we tend to get about 150 dB of shielding just because of the metal. That might not be enough, and they do see backgrounds in the detector from radio. They don't go away with the magnetic field though. So you see there's the signal. Yeah, radio backgrounds are a problem. The axion detectors, fortunately, all the standard models of the axion are pretty much there all the time, whereas radio signals tend to come and go. The other thing you can do is if you've got an antenna and it's inside a 150 dB shielded box and you see something, if you take the antenna and wave it in the air, you'll see something that's a lot bigger. So the other veto that you can use and just basically look in the air, and if you see a massive signal, then it's not the axion. That's the other trick. But you're absolutely right. You do have to worry about those things.
Tony.
Your picture of your detector with the suspension mechanism,
Yeah.
like a multi-tier thing, and you mentioned quantum computing.
Yeah.
That suspension mechanism look like a quantum computer.
Well, the whole thing does. I mean, you see the picture of a quantum computer, they're not showing you a quantum computer. What they're showing you is a dilution refrigerator. Yeah. And it's got a bunch of wires in it. Well, that's just all the RF coaxial cables going down. And what that kind of quantum computers, there's many kinds of quantum computers, but that kind basically contains these things called superconducting qubits. It's a two-state system made out of an electrical circuit that typically contains Josephson junctions, right? And what they do is they take these electrical circuits and they put them inside resonant cavities. Sounds familiar, right? Yeah. So the array of qubits that forms the quantum computer is inside essentially one of my cavities or a similar one. And then they couple electromagnetic signals to the qubit by exciting the resonance of the cavity and using that to write or read the qubits. That's what they do. So the only difference between a quantum computer and my experiment is the qubits. So it's really not so different. You know, and actually lots of the ideas that we're playing with, particularly this one of using a circuit to make resonances, might be very useful for quantum computing, because it might provide a mechanism for write and read the qubits individually instead of all at once. So there might be some work there which could be very interesting and, you know, practically interesting, not just interesting for solving dark matter. It doesn't really have any practical application. You can discover dark matter, people are just pleased. It's no real, doesn't help anybody. It's just kind of, you feel pretty smug because you've solved a problem. 100-year-old problem would be nice to solve it, but it's not going to help anyone. Not really.
Another question, if I may. So, one of your early slides, when you're talking about the Big Bang and how the particles were formed out of it,
yeah,
the electron was on twice.
The electrons are, as far as we can tell, just as fundamental as quarks. And one of the first things to be discovered, and still not a composite, there's no internal substructure as far as we can tell their point light. So they're up there with the quarks as essentially fundamental. So the humble electron isn't that humble. It's been around since very early on, and we don't know if it has any substructure. It behaves like a truly fundamental state. Really interesting. Thank you.
I think I'm just going to wrap up with just one more question.
Yeah.
How long do you see the experiment being able to run for? I mean, ADMX has been around. Well, you said it for 30 years.
Well, you know, I mean, now that I've built it, as long as I can get enough money to repair things when they break, it can run till I retire. You know, at least 10 years. And hopefully by then we'll have hired somebody else and I can potter around a lab as a retired old dude, and they can try and keep me out of trouble while they look for axions with it. I hope it'll be around for a while. I mean, the dilution fridge is the only facility of its type in all of the northeast of England. So in principle, I should get people who are interested in using it. And it's sort of starting to happen. There's a group at Manchester who like axions as well. Now, they don't have a magnet that's worth a damn, and they don't have a dill fridge either. So I'm hoping that they will pay for the privilege of running their axion search in my fridge, which will help me keep the wolf from the door. You can't repair something on a grant. So even if I get a grant to do axion searches, if something breaks in a lab, the university is supposed to pay for it. Well, of course, they don't want to. The only way you can do it is by running it as a facility, collecting money from users, and then make an account, and then that's how you pay for repairs. So I've got to run it like a business, basically. But it's great because the people from Manchester are actually really good scientists, so I can learn a lot from them. So I've got no problem with it. They're really nice people too.
And to finish off, many, many years ago, I think after the second or third time, you came to talk to us about gravitational waves.
Yeah.
And you said, watch this space.
Well, it's been interesting.
So can I push you to sort of make a prediction of when you're going to get a result?
Well, we did discover gravitational waves collectively. I'm now out on a limb, so I'm looking for a type of gravitational wave which would be emitted by a magnetar. You know about magnetars? Yeah, okay. So it's possible, though unlikely, I should emphasize, that magnetars emit essentially a sine wave that changes frequency as the magnetar decays away. And you might get a signal that lasts maybe a few hundred or a few thousand seconds, reasonably high amplitude with that kind of evolution. And it's quite a rapid evolution. And so that falls between stools. The continuous wave people are looking for continuous gravitational waves from things like single neutron stars. They're looking for frequency evolutions at sort of 10 to the minus 7 hertz per hertz. So they're looking for things that are very stable and decay very slowly. Nobody's really looking for things that evolve rapidly. So I am. So I've got a student who's building a gravitational wave search looking for magnetar signals, and he's actually probably about 6 months off having results. And it's very unlikely, but we could find something. It'd be very important if we did, because LIGO's actually seen a whole lot of black holes, hundreds of, and a few neutron stars, but it hasn't seen anything that isn't an in-spiral. It hasn't seen anything that doesn't basically look like a dumbbell. That's the best gravitational wave emitter you can have. Everything else is much less efficient. So when I was trying to get a job at one point in Seattle, he almost lost me. But fortunately, there was this guy there called Eric Adelberger, and he hated gravitational waves, and he heckled me during my talk, so I didn't get the job, so I'm still here. Adelberger's objective of gravitational wave detectors was actually correct. What he said is you'll discover things, and they won't matter. And, the one thing that LIGO has discovered, which I think really, really matters, is that neutron star in spiral that it found in 2017. Because that had an optical counterpart. And so you've got this multi-messenger information, and it solved about 5 outstanding problems in astronomy in one go. And that was really a truly brilliant thing that LIGO did. But all of these black hole discoveries, it really taught us there's some black holes out there. We kind of almost knew that anyway. So there's this worry now that LIGO will carry on just seeing the same old shit forever. And all the other stuff is 3 orders of magnitude down in signal amplitude, and it's incredibly hard work to build a detector which can go there. So LIGO could suffer from just not being quite good enough. That's the worry I have about that. And in order to get around that, you've got to throw a lot more money at it. And you know how it is with experiments. Once they've done one good thing, funding agencies are kind of reluctant to throw more money at it because you've had your bit now. It's a natural human instinct to sort of go on to something else. That's what I've done, to be fair. So LIGO may have a very bright future, but it may also have a sort of slow lingering death future. And it kind of depends on the resolve of people doing the work and the agency and the vision of the agencies. And some of the agencies at the moment don't have very much vision, in particular National Science Foundation, which is unfortunately getting rained on by some people we shouldn't talk about, but I'm sure you know what I mean.
Try not to mention them. I did say that was your little last question, but Tony Morris has been waving at me. So
it was interesting you commented about the lady student who we got this development board.
Yeah, she's great. Her name's Miriam. She's lovely.
So what kind of development board is it?
Oh, okay. So
you got it from Maplin? So
no, a bunch of years ago, I had some money to spend off in a hurry, so I bought this thing called a ZCU 111, which is basically a development board for a chip called an RF system on a chip made by Xilinx. Yeah. And it's a single chip that contains computer cores and then a bunch of sort of digital Lego, they call it FPGA fabric, so you can sort of make your own digital circuit. And then it also contains RF, very high speed RF electronics based on high speed CMOS. So all of those things are on one chip. So everything I need to build axion electronics on one chip. So I figured I'm going to buy this. It looks great. So I bought it and it sat on a shelf for about 5 years. And then in the meantime, I found it was very hard to program. You know, sometimes you buy these complicated things and you realize it's actually pretty difficult to get them to do anything. Well, some people at Fermilab released some freeware specifically for that board. So I found out about that. I knew about it, and then the student came to me and said, "What can I do?" And I've been waiting for an excuse to get that thing going. And I said, "Well, why don't you play with this?" And I go, you know, postdoc's helping. My postdoc Paul Smith is an FPGA veteran, so he knows a bit about this kind of electronics. So between him and Miriam, and I know a bit, we're sort of gradually getting this thing going. So it's you know, it's a sort of fortunate combination of factors that led to it.
I was just wondering whether, because that's in the RF arena.
Yeah.
There's so much RF test gear out there now.
Well, we're making use of it. Yeah, absolutely. We're all over it. Right. The RF, the sort of software-defined radio revolution, that's absolutely brilliant. You know, it's made everything go cheaper, and there's all this work being done, and I'm totally loving it. You know, I've got lots of kit that I've bought from that pile of stuff that's being made. And that's just wonderful. You know, when I started off doing axioms, the only people who were interested in making RF circuits were selling to the American military. So everything was massively expensive and very small. If you wanted one of something, the best way to get it was to just ask them to give it to you free. You just ask for a sample and they give it you for nothing because they had so much money. If you wanted to buy it, they wanted to sell you 1,000 of it. It's a real struggle. But the software-defined radio thing has made it into a hobby again. It's something you can do at small scale. It's wonderful.
Plus, you can characterize it yourself.
Yeah. Oh, yeah. You can get, hobbyist network analyzers now that you can just buy, you know, as long as you don't want to go too high in frequency, it's only a few £100. No, it's made electronics is now a hobby you can enjoy again. For a while, it was basically professionals only, and it's really great the way it's all come back, and you can kind of do your own stuff. It's just you have to know different things now, but not that hard. Yeah.
Okay, I think we've worked, Ed, hard enough this evening. And can you join me in giving Ed Daw a huge experiment in Astronomical Society? Thank you. Thank you very much, Ed.
Yeah, it's my favourite astronomy society. I always love coming, so thanks for inviting me. I'll be back.